Hi, everybody. Welcome to this new video series where I'm going to be discussing how to work with geospatial data in SQL Server. And I will have a few videos. The first one I want to start with is to give you an introduction to what it means to working with geospatial data in SQL Server. And before we can work with geospatial data at all, we need to understand exactly what it is and the different types of forms and shapes that we're working with, and reference systems, etc., and projections and so forth. So I thought I'd start by giving you a geospatial primer. And I have a slide deck I'm going to be working off, and in between, I might go back and forth in SQL Server to show you how you can work with the data there. So let's get started. All right, so here's the agenda that we're looking at least for the first portion. So we'll give you a geospatial primer, and then we'll start looking at the S3 shape formats that are available, which is one of the most popular forms of shape files. And I will show you how you can work with it, how you can export, import, and so on. Then we'll look at how do you transform or reproject from these different type of geospatial reference systems. So we'll take a little look at that. And then I'll just gloss over some tools you can use to work with geospatial data. And then we'll look at some spatial functions that are specific to SQL Server. And then also we'll discuss the index method that are being used for geospatial data in SQL Server. So let's get started. So first thing we want to look for is how to understand degrees, latitude, and longitude. And if you think about the Earth, it's a spherical object. And as you can see here, there is an overview of the size of the Earth. If you look at the size of the Earth, you can see it's estimated to be about 12,756 kilometers in diameter. And that's equivalent to approximately 7,926 miles. And first thing I want to talk about is latitude. What is a latitude? Well, latitude at equator is set up to be at the 0 latitude degree line. So if you look over here, this is 0 latitude right here. And that's the equator. And as you can see, it crosses across South America, northern part of South America, and about the center of Africa. And it goes a little bit north of Australia over here. So that's set to be the 0 latitude degree line. And as you move north of the 0 degree equator latitude line, it goes up to 90 degree north. So that's a positive direction. So it hits the North Pole at 90 degrees north. And if you go south, it becomes negative. So you're at negative 90 degree on the South Pole. We'll get back to this prime meridian. But if you look at this, there's a vertical line and there is a horizontal line. And therefore, it divides the Earth into quadrants. So this might be one quadrant, second quadrant, and so forth. And this is going to have special meaning when you actually work with these latitude and longitudes. So what is the prime meridian? Well, the prime meridian is I shouldn't say artificial, but it's an agreed upon vertical line that stretches from the North Pole down to the South Pole. And it happens to go through the Greenwich Royal Observatory in London, England, because that's what it was agreed upon in the late 19th century. Okay, so longitude. What is a longitude? Well, the longitude, the 0 degree longitude is this prime meridian. And as you can see, it goes through portions of Western Africa, and it goes through the southwest countries of Europe, and it hits this degree line here right through England. So any degree line longitude that is east of the prime meridian is a positive degree line. So it goes from 0 to positive 180 degrees, and which is at the international date line in the Pacific Ocean. If you go west of the prime meridian, you go a negative 180 degree to end up in the same spot in the Pacific Ocean. So it goes westwards from England. You'll have negative longitude degree lines, and eastwards of England, you go and have positive longitudinal degree lines. So what is a degree? Well, a degree is a specific distance that is measured on this circular globe here. So it doesn't necessarily represent a uniform unit of distance, though. As you move from the equator here, with the 0 degree latitude, and you move northwards, you can see here that the longitude lines get more and more narrow as you approach the North Pole and the South Pole. Right around here, which is the equator, the 0 latitude line, the distance is vertical and horizontal for 1 degree distance is pretty much the same. But as you go further north here, the longitudes gets more and more narrow, but the latitudes remain pretty much the same. And you can see it better here. Notice if I use 10 degree as a measurement, like in this illustration, if I go 10 degree here to the, assuming this is the, let's assume this line here is the prime meridian. If I go 10 degrees westwards and 10 degrees northwards, you can see it's almost like a square. So those distances are very similar. And if you move further north, like in the 60 degree, you can see that the longitude distance is much more narrow and the latitude distance seems much larger than the longitude distance would be. And that's, you can calculate here, you can see it here. It's approximately 111.3 kilometers for 1 degree distance vertical between the vertical line, which is the longitude, and approximately the same number for the latitude distance. But if you move up to 60 degrees, this latitude distance is almost, longitude distance, is almost in half, 55.8 kilometers. Now I can show you how to calculate this in SQL Server, and let's look at a demonstration how to do that. So here I'm inside the SQL Server Management Studio, and I just open a file that I have, and I'm just using my SQL Server 2019 version here. And I have a little script here that I'm going to try to illustrate the distance calculations that we talked about. So right here, I created a couple of variables, the equator, and I'm making it in SQL Server. You set the data type to be, in this case, because I'm doing distance calculations, I'm using a geography object. And there's also functions inside SQL Server. And we'll talk more in detail about all this later, but I'm just going to basically illustrate my point here before we start talking about all the details of these functions. So geography has a function called stPointFromText, where you enter some text in. And we're going to talk more about what the meaning of this is later. But for now, this is just representing the something called the WGS84 system, the Geospatial Reference System. So for now, let's just calculate this so you can see my point. What I'm doing here, and keep in mind, when you do calculations in SQL Server, you got to be careful, because according to the way that SQL Server is set up to calculate latitude, longitude points, you start with the longitude value first, and then there's a space, and then the latitude. So longitude is first, then latitude. And you can use a point. You create a point in this case. So let's see what happens here. So what I say is I'm going to be at the equator, and this will be the prime meridian because longitude is first, and this will be the latitude, which is the equator line. So I'm creating a point here at the equator, and then I create another variable that is 1 degree east from equator. So again, longitude, latitude. Again, I'm using the same function. And now I'm saying, hey, I want to go 1 degree east, so that would be positive longitude, and the equator line is still at 0. So then I'm creating a point 1 degree east. And then I do 1 degree north from there, and I'm making a point of, because it's north, I want to stay at the prime meridian, so I leave the longitude at 0, but I go 1 degree north because latitude north of the equator is positive. So I do 1 degree here, okay? And then I can do my calculations by using, by creating this geography object here and this, these two geography objects. I can take the equator and calculate the distance east of the equator by taking the geographical representation of this 1 degree east from equator. And then I can calculate that, and I divide it on 1,000 because I want it in kilometers. I want it represented in kilometers. And then I do the same thing for the northwards. So when I run this now, you can see that all of this, hold on, I'm going to run this one more time. I got too much here, so let me do it again. Okay, so if you look here now, around the prime meridian, you can see the distance in latitude north is 110.57 kilometers. And the distance between longitude, is 111.31. So latitude and longitude are very similar in distance. And that's why you can see the distances here are pretty much the same. So I can also run it at the 60 degree mark. So here I'm simply changing the 1 degree latitude up to 60 degree. And I will run the same thing here to calculate at that point. So if I run that now, you can see it's about half now. And that's the longitude we're talking about at this point here. We looked at the calculations and the degrees, the distances, longitude distances versus the latitude distances. So the next thing I want to do is I want to explain how we can convert degrees into decimal degrees that we use typically for longitude and latitude in SQL Server. So in order to understand that and how it's represented in many places in literature, the longitude and latitude values has typically been represented by angular units of degrees that you divide into 60 minutes and 60 seconds of arc. However, you can convert it into decimal format, which is most likely used when on these maps that we populate using Google Maps, etc. In order to do that calculation, you need to say decimal degrees is equal to degrees plus minutes divided on 60 plus seconds divided on 3,600. So here, let's look at an example. Here is this is taken from the CIA World Factbook, and I picked my home country of Norway. And as you can see, the capital of Norway is Oslo, and it tells you that the geographic coordinates for Oslo, Norway, is 59 degrees, 55 minutes north, and 10 degrees, 45 minutes east. There's no seconds mentioned here, as you can see. So how can I convert that into decimals so I can actually put this onto a map? Well, we have the numbers here, 59 degrees, 55 minutes, and 0 seconds north of equator. So that's the latitude. We got 10 degrees, 45 minutes, and 0 seconds east of the prime meridian. So Norway is east of England, as you can see on the map. That's the longitude. And if we're going to compute decimal degrees, we have using this formula. So if we put in the numbers, we have 59 degrees plus 55 minutes, which is taken from here, divided on 60 plus 0 seconds divided on 3600. This will fall away, obviously. That's the calculation of the latitude. So you're getting 59.99666667. Now, for longitude, we do the same thing. We have 10 degrees, as you can see up here, 45 minutes and 0 seconds east. So 45 over 60, 0 over 3600. So when you compute that and take those numbers and put into Google Map, then you end up right here at this address in Oslo, Norway. So that's how you can convert from degrees and minutes and seconds into decimal numbers. Let's try one more calculation. Let's say you want to figure out the White House in the US. Well, it's located at 1600 Pennsylvania Avenue in Northwest Washington. And according to Wikipedia, it sits at 38 degrees, 53 minutes, and 51.61 seconds north. The longitude is at 77 degrees, 2 minutes, and 11.58 seconds west. All right, so how do you convert that? Well, 38 degrees plus 53 minutes over 60 plus 51.61 seconds over 3,600 gives you 38.897669 in a latitude. Doing the same for the longitude, 77 degrees, 2 minutes, 11.58 seconds. Doing the calculations here, you end up with 77.03655. However, one more thing you need to keep in mind. Whenever you go west of the prime meridian, the longitude becomes negative. Therefore, we have to prefix it with a negative sign, as you can see here. Plunking those numbers into our map, you can see we end up right at the White House here. So that's how we can compute decimal degrees. Okay, now that you've seen how we calculate this, it's your turn. So let's try a little quiz here. All right, let's say you want to find out a point in Australia. Based on your knowledge now, if you look at the options A, B, C, and D here, and think about the prime meridian and think about equator, where do you think Australia will fall? Which quadrant is Australia in? See if you can come up with some idea, and then we'll look at it. So pick a number that you think it is and why. Think about it. Okay, so we know that Australia is down here. So it's the down under is sometimes called down under what? Down under equator. So the latitude, therefore, should be negative. So when we look at these answers here, well, it can't be these A and B because that's positive latitude. So we know those are out. It could be any one of these, C or D. So the next question is, which quadrant is it laid in? Well, it's east of the England, right? East of the prime meridian. Therefore, any longitude should be positive, correct? So it should be a positive longitude and a negative latitude. So when you look at these answers here, both of these are negative, so it can't be this one. So the answer, therefore, should be, you got it, C, negative 30 and 140. If you put that into your Google map, you end up in Australia somewhere. So that's how you can compute these decimal degrees. All right, the next topic we want to look at is projection. How do you project? Well, projection is rather tricky because it's a three-dimensional model of the Earth that you're trying to get into a two-dimensional projection. And any way you try to make that happen, there's going to be problems with it. And the method that is being used is in SQL Server. There's basically 4 kinds of projection methods used. The first one is equirectangular, and then there's a Mercator projection, there's a Robinson projection, and a Bond projection. So if you look at what that will look like in SQL Server, you can see this is what the equirectangular projection looks like. And it's basically flattening everything. Everything is kind of constructed horizontally and vertically accurately in squares, basically. So it becomes very flat as if you look at it. The second method is the Mercator projection. By the way, this is the method being used by Google and Bing Maps, and a lot of books and in geography uses this particular projection. There's also something called Robinson projection, as you can see here inside SQL Server. And finally, you have this bond projection. So, these are different methods being used to represent geospatial information. This particular projection accurately projects points near or at the equator, but it kind of loses its projection accuracy the further north you go. And that's always a problem. It's very popular, this method, and is being used by Google and Bing Maps. So if you look at the Mercator projection, you can see it here. Picture you have a ball inside a cylinder like this, and it's vertically oriented. Then wherever the sides of this ball is touching the cylinder, that is going to be the most accurately measured point if you kind of flatten this three-dimensional object into a two-dimensional object. That's why we say that is most accurate around equator when you use this particular projection, because it's kind of touching the sides right here. So the distance are very, very, there's no distance, right? But the further north you go, it goes inwards. And then when you try to push this to the side of the cylinder, it's going to get distorted. There is another method called the Traverse Mercator that is used for polar regions. So if you take the same cylinder now, leave the Earth in this vertical position, North Pole up here, South Pole here, but rotate the cylinder into a horizontal position. Then you'll see it touches the sides here on the North Pole and South Pole, so it becomes very accurate at that point. But obviously now, this is not going to be very accurate around equator. And that's what's called a Traverse Mercator. Finally, you have something called oblique Mercator projection. That's when you kind of start tilting the cylinder so it touches different points on Earth here. So those are different methods of the Mercator, different projections of the Mercator. So another thing, because of that problem with the vertical cylinder and the north, further north you go, it gets more and more distorted. The Google and Bing Maps, as you can see, they almost cut off the projection because they both use the Mercator projection. They almost cut it off at 85 degrees north and south. So at that point, everything becomes very distorted. So it's usually not very accurate at those places. What projection types do we have? Well, there is hundreds of different ones, and they all kind of trying to do the same thing. They're trying to put a 3D object onto a 2D surface. And no matter how you do that, it's going to be difficult. So here you can see there's different types of cones being used. There's cylinders. There's flattening effects trying to be used. So what's the right method to use? Well, there is no right answer. It all depends. There's pros and cons for any method you use. And there are distortion problems if you use, for example, the Mercator projection. Further north you go or south you go, there's going to be problems. So anyways, that's just something you got to have to deal with. The last thing I want to look at now is datum. What is a datum? Well, a datum contains information about the size and the shape of the Earth. So it holds the details of the reference. What is an ellipsoid? Well, that's the object, the model we're using to represent the Earth. And what makes it different from a sphere is that you basically flatten it on two axes. So picture you have a soft bouncing ball, a small one, and you grab it with two fingers and you squeeze a little bit. You basically flatten it a little bit. And in our world, that would be you flatten the north and the south pole a little bit. And that will be an ellipsoid. Now, what's the advantage of ellipsoid is that it's easy to compute points on an ellipsoid. And we're going to use that to model our Earth. One of the advantages is therefore that the calculations can be done very accurately. So in SQL Server, there are many hundreds of geographic coordinate systems. And you can find these in a view called Spatial Reference System. When you query or run a select star from sys.spatial reference systems, you're going to see what I'm seeing here on the screen. It's going to calculate a spatial reference ID. There is the authority name, and there is the authorized spatial reference ID. And there's something called well-known text that basically lists the datum. And then the unit of measure, as you can see here for the highlighted row, is meters. And its conversion factor is up to 1 meter, as you can see here, the unit conversion factor. Now, I happen to highlight this 4326 reference ID. And over here, you can see the authorized spatial reference ID is 4326 as well. So SQL Server is using the same reference ID as the EPSG. And we'll talk about that in a second. So you can find out the datum right here inside this well-known text. The World Geodetic System of 1984, the so-called WGS-84 coordinate system, is based on the European Petroleum Standards Group, or EPSG. And you can see it over here. It's the EPSG 4326. It's the WGS-84. Okay? So that's the data model that was used by the European Petroleum Standards Group. It's one of the most used methods for geographic coordinate systems. And it's being used by global positioning systems. And both Google Map and Bing Map is using this particular system. And like we said, the measure is in meters and is consistently globally accurate within plus minus 1 meter. So each one of these coordinate systems has their own spatial reference identifier. And the authority behind this is the European Petroleum Standards Group. So SQL Server is using the same spatial reference ID as EPSG. And you can find that obviously by running a query, querying the well-known text from sys spatial reference systems, the view, where the spatial reference ID is equal to 4326. And when you run that, you'll get this, which is the datum information. So what we're going to do now is we're going to look a little closer on this. What does this mean? Well, you see, this is the result from that well-known text. When you run that, you're going to get this. So what does this mean? Well, the GOGCS just stands for Geographic Coordinate System. So GOCS, right? And the datum is the full name. That's the World Geodetic System of 1984, the so-called WGS of 84. The model being used for this particular reference system is an ellipsoid, and it gives you some numbers in here. And what that means is that there's something called a semi-major axis, which is the equatorial radius from the center of the Earth, which is 6,378,137 meters. The radius is. So as you multiply by 2, you get the whole diameter, which we explained in the beginning of this video series. And there's something called a semi-minor axis, which is 6,356,752.314 meters. And the reason for why this distance is greater than this distance is because, remember, we flattened the North and South Pole. We flattened that down. So if you look at it, you have flattened the North and you've flattened the South. So what does these numbers mean? Well, This is the distance from center of the Earth out to the equator here. That's called the semi-major axis, and that's this in meters. This number here is what is called an inverse flattening ratio. So to get the actual flattening ratio, you have to take 1 divided on this number. A lot of these reference systems use this inverse flattening number, okay? So here you can see it. Take 1 divided on that number, that will give you this flattening ratio, which is 0.003353. We know that the semi-major axis, which we call A, this one, is 6,378,137 meters from center of the Earth to equator. So, but what is this distance here? Well, we have to use the flattening ratio together with this number to find that out. So what we can say is to find B, which is this distance, we'll take A, the distance of A, times 1 minus the flattening ratio. And when you do that, you're ending up with this 6,356,752.314 number that we explained. And that's how you can make sense out of these numbers inside this ellipsoid. We know the prime meridian is at Greenwich Observatory in London, England, and that's at the 0 longitude. And we also know that the units we measure in is degrees, but in these reference systems, they also show you a conversion number you can use in order to state the measurement in radians, okay? So in order to do that, you can say that degrees is going to be equal to radians times 180 over pi, which is 3.14, as you know. And you can also convert between these two by saying degrees times pi over 180. And that's how you can calculate between degrees and radians. So now I want to discuss what is shapefile format. Shapefiles is actually not just one file. It's based on the S3 shapefile format, and is geocoded, uses this WGS 84 reference system. And it's not a single file, but a collection of files, of which 3 of them are mandatory, the rest is optional. So you can see it here. The mandatory files is the shapefile with an extension SHP. That is the geometry itself. There's also an index file that comes with it with an extension SAHX. And there is a DBF file, which is an old format that was used by something called DBase 4. And that describes the data that goes along with the shape information. There's also some optional files like this PRJ file that tells you this projection format, which coordinate system is being used. And that's equivalent to that well-known text that we looked at, the Datum file that we looked at before from the SQL Server reference table or view. And there's also a character encoding file that's used by S3 software that describes the characters for displaying the text in the shapefile, for example, UTF. All right, so in order to see those files, what they look like, I have you can look at my folder here, and you can see you have this index file, the SHX file. You have the actual shapes in this file, SHP file. There's also some additional file here that we don't really necessarily going to use. The projection file, for example, you can open that, and that will look something like this. And that's the one that was inside that well-known text field in SQL Server's spatial view. You can see it has the same information in here. And then you have this DBF file, which holds the data itself that goes with the shapefiles. So here's an example of what that might look like. Now, just so you know, you can't really change and add to this file in Excel, but you can do it in Microsoft Access if you need to. And you can also use some other tools to do this, and we'll discuss that later. But here you can see the information that goes with those shapes that I was just showing you. So it has these extra columns. And this is taken from the Census Bureau's zip codes in the US. And you can see here is the longitude. And this 10 at the end here represents that this is from the 2010 census data. Same here for the latitude. You can see it positive because it's north of the equator. It's west of the prime meridian, and that's why it's a negative. So just looking at this, you should be able to figure out where you are in those 4 quadrants. Okay, and over here, obviously, you can see here's the zip codes. Okay, now I want to just talk a little briefly about transformation and reprojection. And if you go to the EPSG, or the European Petroleum's website, there's all kinds of datums. We've mentioned that before. You had all kinds of spatial reference systems available to you, hundreds, right? So here is one. This is the datum for the Luxembourg 1930 projections. And as you can see here, this information should kind of look familiar to you. There's some new things that you haven't seen. It has some values in here. These kind of describes how much you should shift northwards, eastwards, or westwards, and also these numbers are being used to convert this or transform this reference system into the WGS84 system. So when you look at that, you can see there is some reference to WGS84 up here. And if you take those numbers and you want to say, switch them into a different reference system like this Deutsches Hauptdreischnet. I don't know how to pronounce that. Hauptdreischnet. These are the translation parameters you have to use. So as you can see, it is on the x-axis, you have to do a negative 582 meters, y-axis a negative 105 meters. So there's like rotations and shifts and stuff they're using to get to the WGS84. So what happens is you'll have something like this. So this datum from Luxembourg 1930 is converted into WGS84 by using these shifts and transformations parameters. And then from that datum, you move it into this target datum by using these transformation parameters. So that's how you can convert from this reference system to this reference system. Now, we're not going to spend time on this. I just wanted to mention that so you kind of have an idea how that happens and what the purpose of those numbers are. So what are some of the visualization and transformation tools you can use? Well, you can use something called proj.net. There's also this QGIS, which we're going to be looking at a little bit later. And along with this QGIS, as part of that install, you'll get this Geospatial Data Abstraction Library, also called GDAL. You can use the .NET framework for SQL Server stuff, which basically the SQL Server Spatial is written in the .NET framework. It's called a CLR. That uses CLR functions inside SQL Server. There's also commercial mapping tools like Manifold, FME, and of course, ArcGIS. Some free tools you can use. This QGIS that I'm going to be using is a free tool. This Ogre to Ogre is part of this GDAL library we talked about that is part of this install. There's something, if you have old Microsoft SQL servers like 2008, you can use this Shape to SQL tool that is free. You can look that up on a Google search. There's also something for Oracle, Shape to SDO. There's something called GeoRaptor in Oracle. You can, of course, use SQL Spatial. And SQL Server Management Studio also has geospatial rendering available, and we're going to look at that as well. So now let's look at spatial functions that comes with SQL Server. SQL Server spatial data types, there are 2 of them. One is geometry and one is geography. Something called CLR types or Common Language Runtime data types. And they're part of the .NET framework. And they get loaded into SQL Server as CLR type objects. The geography and geometry types can be divided into these 7 subtypes. You can do a point, a line string, polygon, multi-point, multi-line string, multi-polygon, and geometry collection. There's also some new ones that are, after I created this slide deck, there are the circular things you can do as well. I'm not going to be covering that. The geometry data type does not need a spatial reference ID because it's not necessary. It's a geometry object. Geography, you need to state that you're using this WGS84 reference system, which is 4326 in SQL Server. So you need to use it for that. So here you can see geography version of this, STGM from well-known binary. So this is from well-known binary. You're passing in a geometry shape, and you're converting it into a geography shape by using this particular function. And it's in the CLR objects, you do that by using these two colons, okay? So geography, colon, colon, and then the function here. Pass in the geometry object, and it is converted into binary format and use this reference system. And for geometry, you use the geometry prefix, and same thing, geom from well-known binary. Pass in the geometry shape, the column, if you will, and then make it binary. And you can put a 0 in here because it doesn't care, because it uses a Cartesian plane to calculate everything. So let's look at some spatial functions. SQL Server, as you can see, supports a set of methods on geography that is defined by Open Geospatial Consortium, or the OGC standard. And there are some extensions to this that Microsoft has added. And as you can see, they implement the geography spatial data type as a .NET common language runtime, like I mentioned earlier. So one thing to keep in mind is that all those CLR data types are case sensitive. Normally in Microsoft products, you don't necessarily have case sensitivity, but here you do. So you have to type it exactly as you see it down here. So if it's a capital STM, you have to state it as such. Otherwise, it's going to give you an error. So if you look here, these functions listed below here, these are called static conversion functions. So you can see there is something called st point from text. You have line from text, poly, meaning polygon from text. These are some of the more common functions that you might work with in SQL Server, these static conversion functions. You can go and do a search for SQL Server geography functions. And when you do, you're going to see this. So if you pick this OGC methods on geography instances from Microsoft documentation, you end up in this page. And in here, you should be able to find all these different functions and information about it. So make sure you go and check this particular website out and read up on all these functions and how they're being used, and look at some of the examples that they give you here. All right, so those are some of the more common used static functions. We can also nest these CLR functions. So you can basically execute one function after another with this dot notation. So as you see here, I got a geometry object, and I use this st envelope function, and then I nest from that result. I find the st point n function, and then stx. These functions you have to kind of look at, and in order to understand what they do, you have to kind of visit that web page that I showed you. So here is some list of some commonly used functions. This geom from well-known binary I use quite a bit, particularly when I do change one shape into another shape or aggregate shapes and so forth. I use this quite a bit. On projects that I've been working on before, we use this all the time to transfer from SQL Server into maps on the front end in the UI. There's also some, we saw this ST as binary before in that example I showed you. There's also centroid, envelope, distance, and a bunch of points and buffer functions. This one intersects I'll be using later, so you'll be seeing that. And union aggregate functions. So these are some of the common functions that you might encounter. Now, when you're working with shape objects, it's very difficult to work with some of them because they're very detailed. And if you're trying to load a lot of polygons onto a map, you might have some issues with because it takes up a lot of memory. So one very popular method for reducing the shapes is this Douglas, I think it's pronounced poker algorithm. And the way that works in a very simple and maybe oversimplified way is that you might have a shape like this with a bunch of points on it. And this method, the first pass it will use is to start at the first point and go to the last point. So you draw a line from the first point to the last point. That's your first pass. Then what you do is you're looking for the point that is furthest away from the line. It's not totally accurate because this point appears to be a little further from the line than this point, but I picked this one. So the second is to actually draw a line from here to here, which you do in the second pass. And then, of course, you have the line up to the last point here. So you draw a point from here to here as well. And then in the third pass, you look for the distance again, that is somewhere here. And therefore, you draw a line up there. And then you have, of course, you have to hit this point and then this point. So you get in the idea. So you're removing a bunch of points. Here is only 4 points now versus all these other points. So that's a reduce algorithm that is very commonly used. Okay, let's take a look at how SQL Server uses spatial indexes. A spatial index in SQL Server is a little different from the other types of indexes you find there, in that it's basically a grid layout, and you can put a spatial index over either a geometry data type or a geography data type. It allows, therefore, spatial queries to run much faster and much easier, and it filters out the records that are not fitting within that grid. So how does it work? Well, you might have a spatial query that is trying to find all the records that intersects a particular polygon. So by using a spatial index, you can improve that performance because each point will be located within a certain grid area. So what is these grids? Well, they are layers. There's actually 4 layers. And if you look in this illustration here, you have level 1, level 2, level 3, and level 4. So what happens here is that depending on how much you subdivide these layers, here you see a 4x4 level 1, and you see a 4x4 level 2, and a 4x4 level 3, and a 4x4 level 4. So out of this first grid cells, the last one in the first row, you can see it's further subdivided into 4x4 for this level 2 and so on. So you can granularly make it smaller and smaller and fit the data points within these level 1, 2, 3, and 4. So obviously you locate kind of the area where the point exists in level 1, and then of course you get it more and more exact as you go out through these layers, level 1, 2, 3, and 4. And you can further set the granularity of each one of these layers, you can choose whether you want to be low, like 4x4, like these are the one in this illustration is, or medium, 8x8, or a total of 64 cells, or a 16x16 layer, which is the high. So that gets very granular. And you can see here, this cell is cell 15 in the level 1, and that's further subdivided in 4x4 here. And the cell that you're looking for is this 11th cell. So you have 4, 8, 9, 10, and 11. So that'll be from level 1 is 15, and then level 2 is 11. So it pinpoints exactly where the points you're looking for are inside the SQL Server setup here. Also, you'll have some way of looking at these. There is something called SYS Spatial Index Tessellations Catalog View. And if you go into SQL Server and you open up a query window and you type this query in, you can run that. And when you come back, you're going to see I already have some spatial indexes created for both geometry types and geography types. And in the geometry spatial index, as you can see, it basically puts it into the square that has the lowest and the highest x values and the lowest and the highest y values. And it basically creates a bounding box. For geography, you don't have that, as you can see. Here you can see these layers I was talking about. This is layer 1 grid. It was based on the medium, and that was the 8 by 8, and therefore 64 total cells. And then you have level 2 was a medium, 64 cells. Level 3, medium, 64 cells. And finally, level 4, I should be reading this column, not this column, is also 64. So you can see each one of these level has 64 cells in it. And that's how you can find out the granularity of the spatial index. If you look at the actual table in SQL Server, this is what you're going to see. If you put in design mode and you open up a spatial index, you can see it will tell you the bounding box. So this is geometry index. It follows a Cartesian plane. So therefore you have x minimum, x maximum. So negative 180 to positive 180 because it's still geospatial data that is just saved as geometry objects. And you might recall that from the prime meridian, you can go 180 degrees west and east. So that's where you see these. And of course, going from the polar regions is negative 90 and positive 90. And you can see here level 1, 2, 3, and 4 are medium type of spatial indexes. So that's how you can look at it. And then you have the geography index here. There's no bounding box for that. Remember, it was null. And then you can see cells per object is 16. And that's how you can read the information from a geospatial table that has a spatial index on it.